Welcome, everyone. Thank you for coming to my talk. My name is Yasin Reski, and today I'll present you on how to get ready for 16 KB page size on Android. So 16 KB memory page size, in short, has been added on Android 15, and it allows both the OS as well as supported hardware to support this memory page size. In terms of development, you don't need to have a different APK. One APK will be able to work both on older devices that support 4 KB page size as well as 16 KB page size. And we have been deprecating some macro, which in short is the constant that tells you this device is 4 KB page size. Well, we removed that and we have now a function that just runs at runtime. And later this year, we're going to have the Google Play compatibility requirement, so your app will have to eventually be compatible. And that's it for my talk. Thank you very much. Obviously, I'm joking, but in short, is when I was considering this talk is, to be honest, that's what we've added. And I don't have that much more to say. So in short, I'm like, let me explain how memory can work. At least it makes it interesting, especially that I know a lot of you can be Java or Kotlin developers, so you don't really care about memory, which is not great, by the way. We have the profiler on Android Studio. How many of you have used the profiler before? Wow, sorry. But okay, that's a good thing. Adarsh and my colleagues would be super happy to hear that. But in short, what's this change? What's even a memory page? I started by that. And I'm not a native developer myself. I'm more of a Kotlin developer. So when I started, I'm like, I have no idea. It's just a page. I guess it's just a chunk of memory. And after that, I started to ask myself the question more like broadly. So how to allocate memory, all right? And after that, from there, I was like, wait, so if the whole memory is chunked as pieces, does it mean whenever I create a variable, an integer, or I don't know, a boolean, will it take 16 KB 16 KB in memory? That's quite a lot. And I start to think like, wait, how does the CPU access even the memory? Like, I started to go more on a hole and kept digging there. And after that it was, wait, does the process write directly to the RAM? Because for the folks who have been playing with I/O on storage, for example, whenever you do allocate bytes, I think it's in java.io, or if you have something similar on C++ with fopen and writing directly on that part, it's direct. But does RAM works like that? I did study it in computer science. I may have slept on that course, so maybe that's why I don't have already all the answers. And after that, I started to ask myself a question. So wait, bigger size of page is better, I guess? And after that, I just start to think there's way too many questions to ask myself for. Like, at some point, you just ask yourself, like, hey, does it even make sense? You just keep asking yourself questions, and you just never stops. So let's start with the basics. At least we'll be able to understand that. So as a disclaimer, my talk is overly simplifying stuff. So if there is any memory nerd or expert, please forgive me. I may have mixed the concepts and just made it easier, at least for me to understand. And if there is a problem, just blame Gemini. So when we start to talk about memory, there is actually two types of memory. There is physical memory, which is the actual RAM. So I don't know if you remember, if you had a desktop computer, is the long bar that you actually push and hope that you don't break any pins. That's the RAM. So that's where we actually write data on it. But RAM is not directly accessible by processes. So normally the kernel with the CPU accesses it, but as a process or any of your app doesn't write directly to the RAM. If you've worked on embedded computing, that may be a bit different just because resources are constrained. So they make sure that they remove a lot of safety there just to have the best performance for a really limited resource device. And physical memory is chunked in small pieces, and those pieces, we call them frames, memory frames. You may see those different words. And lastly, the frame size, so those chunks, are decided by the CPU. So RAM is kind of like agnostic in terms of how it can be chunked. It's the CPU that decides that. So you may ask yourself, why the CPU and not just the OS? It's actually both. But given that there is a lot of optimizations done at the CPU level, those chunk size are decided by the CPU architecture and design. So after that, we have virtual memory, which is the thing that your processes, your apps actually access. So it's kind of an abstraction over physical memory. And the way you have to understand it, it doesn't mean all the memory written there is directly on RAM. Maybe you may have seen that on, oops, my bad. You may have seen that on Linux. You have what we call the swap, which in short is just a big file that you may have on disk, so on your SSD, on your hard drive. And whenever you use too much of your memory and you don't have enough anymore, the OS will just try to access it. But obviously, your hard drive, your SSD are way slower than RAM. So whenever an OEM will tell you, hey, we got those extra 2 gigabyte of swap, so you have this extra amount of RAM, it's not really true. So it's just a good way to optimize performances on a limited device, but it's not a real RAM. And these chunks, we call that a page, so a memory page. Finally, you were able to understand as much as me. Oh, I really need to stop using my hands. What's a memory page? And the page size here is usually matching the one that you have on the physical memory. And as soon as I understood that, I'm like, all right, so wait, what was the 32 bits, 64 bits thing? So what happens is in your RAM, in your physical RAM, you have potentially, for every bit of it, an address where you can write bytes on it. So from 32 bits, so from a certain limit of of addresses, we moved to a 64 bits where you have more potential addresses. That means you have 2 to the power of 64 addresses, which is 18.64 billions of potential addresses. Obviously, most systems don't use them all. It's just that's the hard limit of a 64 bits in terms of memory addresses. And that's the really, really, really long number if you really want to be precise. So what does it mean is whenever you, as a process, as an app, is requesting data from the RAM or writing in it, you write into this virtual memory. You don't see it, obviously, you just have an address, a pointer, for example, and the system will try to match that with an actual physical memory when it can. The CPU and the OS and the kernel make their own mayonnaise there, so you don't see it. That's really kind of low level. And after that, I was like, all right, okay, I got it. So you have this kind of big table having a mapping, kind of like a hash table. Obviously, it's not that, but it's just a hash table of on one side, your virtual addresses of memory matching to a potential physical memory address. And the CPU knows how to look in between both and can get the data back to your process. This is literally what's happening. So this big hash table is called a page table. So here I'm going to take an example of having an app that tries to read 10 kilobytes of data from memory. You have your process, it asks the OS, please, I want to read that data. But I'm going to keep it first, in the first case, on a 4 KB memory page size. So I don't know if you remember, initially I mentioned 16 KB memory page. In short, on Android, currently we're at 4 KB, and we're trying to make that bigger. So it means whenever we're trying to read or write data, we're trying to get this bigger buffer of data being sent or received at one time. So you as a process, as an app, whenever you're trying to read those 10 kilobytes of memory, you'll ask the OS will try to check in that big hash table if the data exists. In this use case, I'm going to make the worst use case just to see just for you to understand the optimization that this change will bring to all the ecosystem. In this case, I don't have the data in RAM. So you remember earlier I mentioned the swap? Imagine all the data is in the swap because you already used a lot of memory somewhere else. So rather than getting you the data from the RAM, the OS will say, oh, okay, it's not in RAM, so it's probably in the storage, so in your SSD, in your NAND or hard drive. Let me look for it first. We call that, the fact that it has to go to the storage, we call that a page fault. And whenever you have a page fault, you have to understand that you're getting a kind of a performance penalty, like you're wasting some CPU cycle trying to do that work. So you get your 4 kilobyte of data from storage, you put that back into RAM, and you're getting back the virtual address of that mapping to your process. But I don't know if you remember, earlier I mentioned we're trying to get 10 kilobytes of information. So we have to do a second step. Same thing here again. We have to go and check. It's not in the RAM for the second part of that 10 kilobytes. We have to get it on the page table, and we do all that process again. But because it's 10, so we have to do 3 times that journey. At some point, it looks really, really long. So obviously, computers are super fast, but this is what's happening behind doors. So now, with 16 KB page size, it's kind of amazing. You just have to do it once. Great, perfect. So in that case, if 16 KB, given being a bigger buffer, transporting data is better, why don't we have 1 megabyte page size or 1 gigabyte? Actually, some CPUs support that. Some CPUs support 1 megabyte, 2 megabytes, even 1 gigabyte, but those are kind of edge cases. They are not always used. And you have to keep in mind, I don't know if any of you may have had a Windows computer before. You remember the defragmentation where we're trying to get all the bytes moving and we're thinking we're super smart doing that? Well, what happened is when you're trying to get bigger chunk, it's really hard to allocate smaller chunk in between. So whenever you get too big one, it's actually hard to find another empty piece to allocate your new chunk, your new frame. That's why having it not too small, not too big is kind of like the right spot. So back to this really big screen with all those questions. We know what's a memory page, how to allocate memory. Does a process have write access to the RAM? Not directly. We mentioned the virtual memory. We know how the system handles the lack of memory with the swap, and why a bigger page size is better. But let's come back to the question, how does the CPU access memory? So the CPU itself has this kind of concept of caches. You may have heard L1, L2, TLB. Those names, like I knew them, I never knew what's the meaning or why they're important. You have to understand the CPU is being a really, really fast, but also really stupid in some way, piece of engineering, in a sense where it just set of assembly instructions and just try to read from a register to another, and that's how limited it is in some way. So same thing here. Whenever it looks at this big hash table containing all those mappings, it has to do that work every time. So whenever it just did accessing one virtual memory, it wants to remember that physical memory address in a small cache near it, to just be a bit faster. We call that the L1 cache. So imagine again here another hash table, bit smaller, but much, much, much faster, just next to the CPU. Given the limited size, at some point, the CPU designers were like, why not adding a second one? That's your L2 kind of cache. I'm really simplifying. Again, for the ones who are really good at that, please don't throw me tomatoes. I'll take money anyway. And from L2, we went obviously to an even bigger cache named L3. So again here, bigger size, but bigger size means more performance cost because it has to go through all of it. So whenever the CPU cannot fill the L1, it tries to go to L2. If it can fill L2, it will go to L3, and eventually it will go to the bigger page table. So all of that for you as Kotlin developer, Java developers, is completely transparent. You don't deal with it. But for anyone who really care about performance and really trying to touch all of that, that's what your game engine, that's what your custom memory allocation libraries do. They really try to customize and map, how can I say, the best way to use your CPU resources based on what's available. So again, good thing we don't have to deal with that, but folks in the 80s and even 90s were dealing with that. And our friends who are still in the embedded ecosystem, they do that every day. So good luck for them. So now the last question is like, so does an integer take 4 kilobyte or 16 kilobyte in RAM? So in short, in the same way I showed you, we have these big page table handling memory per process. We have kind of the same thing within processes. So on Java, obviously, you have the garbage collector handling all of that. For C, C++, Rust, there is some part of the language helping there, but in short, they have to deal with that memory management. So in the same way, it's also allocating chunks within its own process. It doesn't create a chunk for every single variable, fortunately. So we answered all those questions, and I don't have that many minutes, so now I'm going to be much, much faster. Sorry. So what are the performance gains? So all of that, again, really raw, detailed, low level, but that's not something that you will have to deal day to day. It gives us directly a minus 4.6% in terms of reduced power. So why we're doing all of that? It's on the same existing hardware that will be compatible. You will have less power usage because you're wasting less cycle looking at that page table. You will potentially even save time trying to load memory and write memory in it. Your camera will load faster, and potentially we saw up to 30% of faster up launch time. We know eventually that will impact the rest of the ecosystem, but now we're just doing it at the system level, and we're asking you now to do that migration to benefit the rest of the ecosystem. So how to migrate? First, you need to make sure you're using AGP 8.5.1, and if you've watched the debugger session from this morning from my colleague Fabien and Adarsh, you will know that having newer tooling helps you also within your day-to-day developer life. But here, to benefit that and to have the right compilation tool available, make sure you update to that version at least. You also have to align your native code. So any of your native code that has assumption that you only have 4 KB page size in your memory, you have to modify them and use the function runtime. Otherwise, you will have those potential troubles whenever you will be launching or compiling your app. I'm skipping some items here just because I don't have a lot of time. And of course, if you're using any native library or dependencies that are containing those codes, you need to make sure they're compatible. We have some tools for you to check that. We're going to update eventually also Android Studio and Android Vitals on Google Play to help you find them more easily. But make sure to double check. We have some online guidance to help you on how to figure out which dependency is a blocker. So as I mentioned again earlier, if you're a pure Java Kotlin developer, you're good to go. We already did the job for you. Thank you very much. But in this case, again, make sure that maybe one of your dependency or libraries might not be native. Sometimes it's a dependency of a dependency. So make sure to double check. We also have the online guidance to help you there. For apps with native dependencies, again, make sure you update them and that they're ready. Otherwise, contact the vendor or the SDK developers and maybe even contribute if it's an open source project. I highly encourage it. And lastly, if you're a native app, as I mentioned, the work there may be a bit tougher, but it's much lighter compared to the 32-bit to 64-bit migration we did a few years ago. Don't forget testing. I think that's super important for us and for you to make sure that you're not having surprise on older devices or even, again, those upcoming 16 KB hardware that will be coming. We already worked with a lot of popular libraries, including the ones using multi-platform ones, like the one shown there, and they're already compatible. So We know that a lot of developers are in that area, and we want to be sure they're ready for that part. Lastly, I don't have a lot of time now, Google Play compatibility requirement. So eventually, later this year, we'll announce it, and apps will have to be compatible with that. And eventually, your apps that are not compatible won't be able to be installed on those new hardwares. So again, make sure to be ready before then. You don't have to wait for the announcement. You can already upload a 16 KB APK or app bundle. And we've already worked with SDK vendors. If yours is maybe less known or you have a special relationship with them, we highly encourage you to reach out to them. And yeah, now it's for real. Thank you very much.